catalyst today, right?
Yeah, we're going to do that using the slank line. This is where we do air and water-free chemistry. And today we're going to do colloidal synthesis, where we create metal nanoparticles using ligands to steer their size and their shape. So I'll show you how. Now this is black, indicating we have metal colloidal nanoparticles. Now that I show you how I make my metal nanoparticles, if we deposit them on the support, we can actually use it as a catalyst. Do you want to test this for me?
Yeah, sure. Let's go.
So good luck with testing.
Yeah, thanks. Hello, Sebastian.
Hey, Matteo.
I have a catalyst to test. Can you help me?
Of course I can.
We can even watch it come to life by using operando spectroscopy.
What is operando spectroscopy?
Well, with operando spectroscopy, we have a little camera right here that we can insert into our reactor. We look with the special camera and then watch the products come out. And I use it, for example, for studying coke. And the nice thing is, we can even do it at high temperature with the setup.
Did I hear you say high temperatures? So these kind of reactor tubes are the ones that we use in this setup to do our testing. But of course the average reactor temperature can vary quite a bit from what's going on inside of this tube. So that's where luminescence thermometry comes in. If we include a luminescent ion inner material, here I can show it to you. If we excite this with a UV light, you see some very nice red luminescence. We can actually use that to measure the temperature locally on the surface of the actual catalyst.
Hey Florian, I already know a lot about my catalyst now, but maybe you can tell me more with this setup?
Yeah, sure. Matteo, you can use the operando RR to study surface intermediates, and that is really helpful because you can study the reaction mechanism, and you can also study indirectly the surface species of your catalyst. So at this setup you can, for example, test the CO2 hydrogenation, but also other reactions like, for example, methane oxidation. And we are able to study a variety of reactions by applying a multitude of gases at the same time.
Hey Bas, how's it going?
Hey Matteo, good. How are you?
Good. Can you tell me what you're doing here?
Of course, yeah. So I was actually just about to load a new reactor into my setup. So actually I'm doing something that is complementary to what Florian is doing. So in this setup we can use Raman spectroscopy, which is also a vibrational spectroscopy technique, but now to study the catalyst instead of the catalyst surface. So what we can do is we can look at the vibrations of the catalyst itself, and we can observe, let's say, phase changes that occur during the reaction. So for instance, in the reaction that I'm doing, I'm using hydrogen chloride, and this affects the state of my catalyst. So for instance, I have a lanthanum oxychloride catalyst in this reactor, and if we react it with HCl, we can see a phase transition from the lanthanum oxychloride to the lanthanum chloride. And that is something that we can observe with the Raman spectroscopy.
Hi Ina.
Hi Matteo.
So I learned a lot of how we can use light to study reactions, but we can also do other things.
Yeah, we can use the light to actually drive the reactions, and I will tell you more about that now. Okay, so follow me. Let's see what Miriam is doing. Hi Miriam.
Hi.
So can you tell me a bit more about what you're doing here?
Yeah. So here I'm building a setup where I can test nanomaterials that can perform catalysis using light as an energy source, in other words photocatalysis. This is still a work in progress, but I've already made a design of the setup that I want to build. And actually we already have one of the most important parts here, which is the solar simulator that can imitate sunlight. So I can shine this solar simulator, a lamp, on a reactor containing a photocatalyst and initiate photocatalysis this way. And I also want to use other light sources such as LED lighting that can simulate room lighting.
Right, so another way to study these catalysts is by studying the charge carrier dynamics. We do this using transient absorption, this setup. This setup uses two pulse lasers
to excite, to create these charge carriers, and by changing the time interval between these pulse lasers, we can get an idea of the charge carrier population over time. And if we know how these carriers or these charge carriers behave, then we might possibly favor these dynamics for a certain photocatalytic reaction. So another really cool feature is that we can place our photocatalyst materials inside this cryostat and place this inside the transient absorption setup so that we can also study the effect of temperature on these on the charge carrier dynamic.
Hey Cordula, hi! So far we have talked a lot about powders, but you're working with quite different materials.
Yes, I'm working with thin films, and thin films can be analyzed on very different techniques. So one, for example, is the GI technique. So we have here two different arms which can rotate into an angle and then analyze the thin film surface of the material. On the other hand, if you don't want to have only the crystallinity of the surface, we can also do GI-ATR. Then we go over there. So when we're looking at our sample, we can look at the surface of it like with this GI-ATR. So it works in principle like a normal ATR, but with the grazing incidence of the beam, which then makes us able to only analyze the upper layer and even make it possible with differing the angle which is incident, so the same angle differs then we can make even a depth profile of the whole sample. So with this we get the information about the whole sample of our surface. And if we would like to get really the spatial resolution information, the chemical information, we would have the atomic force microscopy over here. So with atomic force microscopy we can scan over the whole surface of the sample, and at each and every pixel make a spectrum like we did before with the GI-ATR. So we don't get only one spectrum here, but we get one from every pixel of the sample. Which is really nice because then we get from every part the chemical information of